Now you're done with your root cause analysis per part and per assembly as needed based on your change matrix. Here we're giving you some kind of steps to avoid the concern by taking some examples on that. So here you're having a root cause on the left side and you're having steps to avoid that specific concern. It could sound simple, but it is something to follow as you're moving forward. So you finished your root cause analysis for the specific concerns or potential concerns that you identified in your change matrix. Let's say one of those concerns you have undefined tolerance in your design. Then we would say steps to avoid the concern: define tolerances as detailed as possible. This way you can avoid concerns. Then you go back to your change matrix and make sure it's not a concern anymore after doing the design review with the experienced members. If you have in your design low material stiffness in your part, let's say, then we would say increase your material stiffness and see if that would help avoiding that concern. If you have a root cause as unclear position for that cause, then simply define clearly the cause position in your part or in your assembly, let's say in a Cartesian XYZ. So the more you define and the more you clarify the details for design and physical properties for your concern, the better, and that make it easy to avoid that concern and eliminate it out of the concern matrix in the change matrix that we have. For potential causes, we have two types of causes, either a controllable causes or uncontrollable causes, which we call control or noise. So control is parameter with adjustable nominal values. You have, for example, design parameters or process variables. Noise, those are things that you can't control, sources of variability. It could be internal or external to the system. And that could be as environment or the customer use or the process variation. Let's say you are designing a vehicle. This vehicle is having a new design, engineering side, and even the outer design side. Now you have an environment that you want to deal with. This vehicle will be running in a cold weather or it will be driven in a hot area. Then the environment is uncontrolled variable. You want to deal with it as it is. You want to adjust your system, your part or your assembly to handle that environment. Customer is using the product in a certain way and you can't force the customer to use it in a different way in most cases, let's say. So in this way, you want to adapt your product or your design to be suitable for the customer use and the way he's handling your product. Process variations, sometimes in the process there's many parameters that getting varied along the process. You need to keep those in consideration to be able to deliver a durable product and being able to handle all the potential concerns that you have in your DRBFM process. Now giving you tips and tricks on the root cause analysis. In order to do your root cause analysis as straightforward and as efficient as possible, firstly, you use simple and direct description and you ensure the simplicity and clarity throughout the detailed explanation. As simple as possible, as clear as possible to be able to tell the story, as we said before. Then you locate the controlled factors versus the noise or the uncontrolled factors. And eventually you identify the potential causes from various perspectives. In this case, you're looking at the environment that the product is in. How does this part is interacting with neighboring parts? How does this part is handling certain physical parameters or certain sequence of testing to validate that product? In this way, your root cause analysis will be as straightforward and as efficient as possible. And make sure when you're working on your root cause analysis to address each root cause with design evidence or engineering studies, such as design check sheets, benchmarking results, hand calculations with predicted safety margins. This way you try to avoid the concern as much as possible. Then you need to make sure to link each identified cause to whatever supporting documents or whatever online supporting information that could help in identifying that cause or supporting your claim of mentioning that as a cause. They need to show a completed items plan, no future plans. I mean, we said you can do future predictions. That's the whole process is about. You do future predictions and try to use your best practices to tell if this product will behave in that certain way. But when you show the parts in your product, you don't show parts that could be implemented in the future. You need to show the exact real parts that's happening right now, or at least the design that's mostly going to be approved at this point. There's no future plan. Then you need to be quantitative so that you can clearly satisfy the function and requirement. You want to make sure you have all the estimations and all the supporting data that will show that you are clearly satisfying functions and requirements of your customer or your supplier and so on. Then you need to be extra careful with using the computer-aided design or CAE or 3D design, whatever you call it. And that happens by including inputs, assumptions, and boundary conditions that used, and eventually you clearly show the results in your final reports coming out of those CAE so that the experts can identify if the process been used in creating CAE supported analysis are valid and good to go to be used as a solid reference in identifying causes and clearing out concerns.